Hello friends, it's me again, Dr. Patterson. In this video, I'm going to go over the main topic for week 7, which is essentially taking stepper motors, uh, or what we were doing with stepper motors in week 6, and looking at it from kind of the next level up. Right? And so in lab, we created the home function, the fast move function, and the coordinated move function. And now we're going to essentially use those to perform more complex tasks, which could then, hopefully in next week, we'll be able to further build on that thinking and perform even more complex tasks than what we're doing this week. So stepper motors, incremental steps, right? Where I talked about using them to make different CNC type devices, so 3D printers, anything you can attach a tool to, routers or mills, lathes, um, laser cutters, any kind of water jet cutter. These are all things that are commonly controlled using computer numerical control, which is essentially relying on some type of computer or microcontroller to process incoming commands and correctly calculate the movement of motors, whether in an open loop system like we're using right down here, or in closed loop systems like the fancier industrial machines use. Um, Again, just another 3D printer. Um, and the three functions that we made in lab were the rapid move, which was G0. So that was moving from one point to another. There's no coordination between motors. We just try to get there as fast as possible. There's a linear move, which is coordinating all movements so you can, in Cartesian space, draw a straight line from one point to another. Really, the goal is starting and stopping motors simultaneously, and they can all move at different rates from each other. And then lastly, the home function, which is a G28 command. There were a few others I was going to bring up too, which was uh, some of the other common ones. So home, you find the reference point that you're going to base all your movements off of. For some of the other commands, there's G20 and G21, which are essentially changing what unit system you're in. So this is inches versus millimeters. There's G90 and G91, which are fairly common. This can help with programming. If you're trying to do any kind of manual programming, sometimes it's much easier to figure out how far you need to move relative to where you currently are. And so G90 is saying use absolute coordinates, and that's what we've written our functions to do, is saying we're moving relative, or sorry, we're moving, yeah, relative to the home position, right? So absolute positioning versus relative. In the relative mode, you're moving, essentially your 0, 0 becomes whatever your current point is. And then let's say you want to move to a position of 2, 3. Well, that's 2 inches in the X and 3 inches in the Y from where you currently are. Most machines just will always start in absolute mode after you've homed, but you can, on almost any CNC device, switch to relative mode. Again, it's easier if you're trying to program it yourself, if you can have some type of motion relative to where you currently are. So if you wanted to machine, instead of a machine a part over here, you wanted to do it over here, you could go 0 on that particular point, even though your machine home is over here. You could find out what the 0, 0 point is on that particular part and then do everything relative to that. There's also, which I'm not going to go into detail on, there's also a whole set of commands where you can set up work coordinates and have multiple work coordinate systems. Those essentially take that to the next level, right? Like you could have multiple different coordinate systems for your machine. And there could be reasons that that would simplify how you process either the machining or printing of particular features. There's also canned cycles, which are essentially combinations of a bunch of other G code commands. Um, the most common ones are like the G80 series, which are all around creating or processing different types of holes. So there's drilling and tapping, there's drilling and reaming and honing. There's a bunch of different combinations that you can put together. And instead of calling like 20 different lines or putting in 20 different lines of G code, you can just call one and it will like do a peck drill for which is like slow stepping down and backing out of the drilling process. And then it'll switch tools over to a tapping mechanism and then tap it. Or if you wanted to ream and then hone, which is essentially like trying to provide a certain surface finish on it. There's there's different ones that you can use. You can even modify them. There's additional macros that you can set up on a lot of machines where it's like you have this set of 20 G code commands that you want to compact down into one because you're calling it so frequently. And that's why I like the G80 series where you end up using it in the CNC machine class that I teach pretty frequently on projects. Because again, you don't want to have to code 20 lines of G code every time you want to drill and tap or drill and ream and then hone a particular circular or cylindrical feature on your part. You would prefer to just write one line of code. So we've got those, and then so the YTable is a new class that we're going to use this week in Matlab. And this one, I wrote it so that it actually can connect to the hardware, which I'll show you in a minute, but it's also got a simulator-based version. And the way that this works is it has all the same functions. Give me a second, I'm going to take a screenshot. All right, so it's got all the same functions from the previous week, right? So home, fast move, and coordinated move. Except it's implemented in C++ and programmed to the Arduino board. It keeps track. It's got all the pins already in there and everything, so you don't have to set up any pins or set their modes. You don't have to toggle pins high or low to actually step. You just tell it what position you want to go to. So for the home function, that literally means you're just calling home. You don't need to send it anything. For the fast move, you're just saying fast move and then passing it which position you want to go to. You don't have to specify what the current position is because it keeps track of that. And then also coordinated move. I'm not going to write it out, but move. And again, you just specify what X and Y you want to move to, and it will take care of that linear interpolation to get from the current position to that next position. So how does this work? Well, let's head over to the C code. So this is not a great G code interpreter, but it is one that I wrote specifically for the hardware that we have in lab, and then I re-implemented it in Matlab class. So let me back up a second. So how does this work? Well, there's Matlab, right? You and Matlab. And there's the Arduino and C++ code. Right, and so the way that this works for Matlab and the Arduino, when we're actually going to move the physical motors, whether you got some stepper motors or in the off chance that you get a chance to go into lab on this, or really just the simulator version, the way that this works is you're sending those commands, right? We've got home, fast move, and coordinated move. And you call one of these functions, let's say home. Well, that sends commands over to the Arduino board and the C++ code, and it's sitting there listening. It's saying, waiting for commands. Right? So it's waiting there for commands. And then let's erase this. So it sends it right here. And then it says, I will process that command. Then I will perform the homing function. And then I will, whoops, send response. Right? And this goes back to here where this piece of code was wait for response. So it comes back and then Matlab says, okay, now I can go to next command. Right? And so the Matlab code sends some type of command, home, fast move, coordinated move, sends it over to the board. The board receives it, performs that operation, sends a response back, and Matlab is sitting there waiting for that response and then goes on to the next line of code. So how does that look in the C side of things? Well, if we go over to that code, we've got a bunch of variables up top that are declared. You probably recognize most or all of these: step pin, direction pin, A and B switches for both X and Y axes. Delay is not super important right now, but then it keeps track of the current X position, the delta. These are all the same variables implemented in Bresenham's algorithm that we did in lab, and then a temporary variable, and then max positions that it never goes beyond this. Actually, I feel like this number's off by a little bit. It might be a little more than 11 inches, but that's super not important. And then we have the inches per step that each time we take a step with the motor, given the belts on that particular hardware setup, it will move 0.009375 inches. So the first thing that does, right, is it starts up. It has to set a bunch of pin modes, just like we do in MATLAB. And then it sets the step direction, or sorry, the step pins to a low value, because every time we step, we need a rising edge signal for the motor drivers, which are these green guys right here. So that's what it does. And then at first, right away, it will home the table. So let's start up the board and give that a try. So I have to plug this in, and then I've got a power supply hooked up over here. Oh. Interesting. I think one of my wires fell off. 1 second. All right, let's try that one more time. I'll tell you why that happened. One of these buttons had like popped out a little bit. So we home the table, and what does that do? Well, the home table homes each axis, so similar to the seek end stop function that we did. And then in the home axis function, it says set a specific direction using the direction pin. So 1, which we know is towards 0. And then while the button is has a high signal, which again is inverted logic from earlier in the quarter for the button, step the motor. So what does the step motor function do? Well, the step motor function says do a no delay step. And that's just toggling the pin high and then back to low. And so the normal state for the step pin is low. It switches it to high, so we get that rising edge, and then immediately switches it back to low. So all we need is that rising edge to just trip the motor driver to say, I should move now, and then it sets it back so that next time we come back around to take a step, all we have to do is toggle that pin high. And then it delays. This is the same function, or carries out essentially the same function as pause in Matlab. Delay in the Arduino C++ code just delays for a certain number of milliseconds. So that's our home axis function. That's what it does right off the bat. And then it starts listening to any information that's being said. And that's what this serial event function does, is it will just wait, and every time that it receives information over the serial port, which again is the communication line between your computer and the board, it goes through and tries to parse what that information is. And you can even see I've implemented this using G and M code commands. And so you send it something like G0, X1, Y1, and it will go to that particular position. So what if we wanted to do that? Let's go over to Matlab and do clear all, close all. And let's save real quick. XY testing. And then we'll create a new XY table. So my XY is equal, let's come up with a better one. Let's just call it XY. XY table. So that creates a new XY table object, which is going to try to connect to the hardware. But we have to specify what the COM port is. So let's look at serial list. I believe it is COM6. We'll find out in a second. So we can specify COM6 on here and see if that runs. So what it's doing right now is actually uploading the code that you were just looking at. Oh, I'm guessing I got this plugged into the wrong machine. 1 second. All right, let's try that again. So serial list. Now COM4 shows up, so it's COM4. Let's run this. So now it's actually going to, well, if I do that again. All right, let's try that again. So I realized there was a problem with the fact that I was recording and trying to capture, use the XY table at the same time. It actually tries to connect to the webcam, which I'm using multiple cameras here. So I had to change my code so that I could record and run this crappy webcam, spare webcam that I have at the same time. So the way that this works now, again, you don't have to specify the second argument because you're not actively using multiple webcams, I'm guessing. So you specify the COM port, and then you can specify which camera to connect to as well. So I'm specifying this third webcam, but again, not important for this lab. Next week, it'll be important. So let's run this now. And when it runs, it first uploads the code to the board, and then connects to the web camera, waits for a few seconds because webcams always take a few seconds to initialize correctly, and then it returns. And now I can actually run that fast move function like I want to do. I'm going to, nope, forgot to allow it to home, then have the power turned on. Let me turn this one a little bit. Make sure you guys can see. Okay, so let's call XY, let's do a fast move to a position of 2, 1. So it moved pretty quick, hopefully you can already see like the difference between trying to send individual steps from Matlab and running it on the controller. It's considerably faster considering there's the delay that I have between steps is 2 milliseconds. And that's on the order of the amount of time that the communication to toggle one of the pins to be on or off from Matlab actually was taking us before. And so the fact that I can now take a step in that amount of time and then take another step, that's much, much faster than what we would be able to get by just doing it directly from Matlab. So if I wanted to do, again, maybe a little bit longer distance so we can actually see this move, let's do that same ratio. So you can see the top motor, the X motor, actually moved longer than the other one. So that's great. Now what if we wanted to do a coordinated move, or let's move to an even position here. Now let's do a coordinated move back to 0. Actually, it makes sense to show this off. It makes sense to be at an uneven position, right? So if we did fast move right now, the motors would move in unison back to 3, and then let's do that. So they'll move in unison at first, and then and then just the X motor will move for 3 inches. So if we watch that real quick. So the X motor continued to move for an additional 3 inches after the Y motor stopped. Now, if I wanted to move back to that position using a coordinated move, then I can do that, and they'll start and stop at the exact same time, but they'll move at different speeds. So they started and stopped at the same time, but this bottom one was moving at half the speed. And I could even magnify that further. Let's go back towards 0. Do 0 for X and 2 for Y. Right? And so 6 times the distance moved for X compared to that for Y. And so what's happening when we're sending those commands? Well, we're going in and going through that serial communication line. We're either sending G0 or G1. And if I remember correctly, we can even do that. Let's send a G code. And let's do G0, X0, Y0. I believe that's the command. Oh, come on. I gotta check my own code. 1 second. Yeah, it was just lowercase s. So let's send that. And we can see that it just moved. And so it's the same thing. G0 is our fast or rapid move. And G1, which we can now do again, let's change this to G1, X6, Y3 like we were doing before. I'll try to hold them in position this time. And run that. Made a lot less noise when I didn't hold it in place. So let's try that one more time back to 0. So now we could send G code, but really I made it so that we can just use those same functions that we made last lab, right? And this is just masking the sending of G code to the controller, which is what's being processed in this serial event, right? Like let's go down, it receives a G code command and then receives a 0, or sorry, if it's G and let's see, first we could home the table. Oh, this one's checking for G28. Again, not the best string parsing setup here. This is the reason I'm mildly ashamed of this code. And then if it's a G code and it specifies an X and a Y argument, it captures those numbers, and then it goes down and it says either do a coordinated move or a fast move. So let's look at fast move. So the way fast move works, if I can find it, is we go in and we figure out what the targets are. It first caps it between 0 and the maximum distance that it can move. And then it comes up with what the number of steps should be. And then it sets the direction. These are all identical steps to what we did in Matlab. It's just implemented in a different language. It comes up with the target based on what the step size is. And then it comes up with the step counts, figures out what the max count is, and then over from 0 to just less than the max count, it takes X and Y steps, right? So exactly what we did in Matlab last week is implemented in the C code. It's just that the delay that's being taken, or the delay that's being used, is 2 milliseconds versus probably on the order of like 0.01 seconds in Matlab between steps. So much shorter time. We're literally moving 10 times faster than what we were doing last week. And then for coordinated move, it's essentially the same thing for Bresenham's. First, we come up with a target, and we actually determine what that is in step increments. And then we set the direction. And if it's a vertical line, if it's the same as the previous position, we don't move. If it's a vertical line, so the X position doesn't change, then it just says do a fast move. I've even got some code in there where I had re-implemented fast move, but I realized that was silly. And then we get to Bresenham's algorithm. So first we get rid of those special cases where it's literally not moving at all, or it's a vertical line. And then we say, what is the change in X? What's the change in Y? What does that make our delta error? We initialize the error value. We come up with temporary positions, and then we go through and we're literally just stepping the motor, recalculating what that error is. And then if that error is greater than 0.5, we step the Y motor however many times needed, and then we subtract off that error. And then after we do that and we get to the final position, then we set the current position equal to the target values. So exactly what we did in Matlab, again, just a different language. So there's small differences between, but really it's the exact same thing. And so when we send this coordinated move, it's doing the exact same steps that we did. It toggles the pin to set the direction. It sets the direction. It toggles the step pin to get that rising edge to make the motor step, because it's sending that signal to the drivers. And then it's calculating how many times to do that, and it does it either in a just do it as fast as you can fashion, or coordinated movement fashion. And then again, the home function, which we could either call the send G code G28, and I'd have to hit these buttons, or we can call xy.home, which is exactly what we did last time, right? And so now we've got these functions implemented in a way that we can have the motors move much faster because of the more precise timing that we get by using this standalone device, which is just focusing on the movement of these motors instead of trying to have it also tie in back to the code that we're running on the computer. So that's the implementation of the XY table in C code. Now, what happens if we wanted to run the simulator, right? Because I didn't have you guys buy stepper motors and stepper drivers. So let me turn off the power on that real quick. And then let's look at the same thing, but for the simulator. And with the XY table simulator, we get, go back up here. We can get rid of the camera code, and instead of COM4, we specify COM99, and that gets us into the simulator. So let's run this and let's see what happens. It pulls up a plot right away, and it tells you a few things. So it creates blocks, which hopefully we'll get to next week. For you can actually use, it's a simulated sensor on there to scan a surface, and there's randomly created stacks of blocks underneath the XY table, right? And then it also has a built-in camera functionality. If you're not in lab, you can essentially use it to take photos, and it brings back an image which you can then process in some way. Again, next week. But for now, we've got this plot. Let's see what happens when we, give me a second, let me pull up that extra screen again. All right, so what happens when we try to tell this to home? Well, the simulator does automatically when it starts up. So it's already at the home position. So that means we can do xy dot, let's do a fast move to 2,5. So the simulator doesn't capture the direct motor movement, but it does change the color of the lines that are drawn. So the fast move option is making any lines in red, and then the coordinated move will draw any of the lines that it creates in green. So it doesn't capture the kind of uncoordinated movement of the XY, the physical XY table, but it does represent the difference between those two movements in color. So if we wanted to do XY table dot coordinated move, and let's move to, let's do 7, 7. Yes, I did mean that. And so we can see that the line then gets drawn over to the point that we wanted. And then we could also rehome the machine, and it'll go back to 0, 0. So same exact functionality that we can have with the hardware, just represented in a Matlab plot. And so those three main functions, the home function, the fast move, and the coordinated move, are the ones that you guys will be able to use to complete the lab tests this week. And I'll be back again in another video, a couple videos, right? One for the lab and then another one for showing you the lab solution. So that's all I've got for this one. See you next time.